we now come to the point where we're actually going to use Newton's laws in a very quantitative way. All right, we're going to do several examples over the next video or two. So we're going to start with this example right here. We have a 60 kilogram parachutist descending at a steady rate of 30 kilometers per hour. So what force does the air drag exert on the parachute? How do I know that air drag is working? Well, first of all, he's descending at a constant rate of 30 kilometers per hour. Now, this is a unit of speed or velocity, right? So if he's descending at a constant speed, then he is not accelerating. If there were no air drag, he would just be falling at 9.8 meters per second squared, which is an acceleration. So I know that air drag is working because he's descending at a constant rate. Now, another key is, first things first, let's pick out some key words. We're going to want to remember his mass. We're going to remember that he's falling at a steady speed, what the value of that speed is, okay? Now, why do I want to know all of that information? Well, what we can say is we know a couple of things right off the bat. First of all, if he's descending at a constant speed, as we saw before with the light fixture, when it's hanging, it's not moving, therefore it's not accelerating. Well, here, even though it's moving, it's still not accelerating. If it's moving at a steady rate, then my acceleration is 0. So F equals ma is going to equal 0. If it equals 0, then I know that gravity is acting down. That means that I know another force must be acting up. What is that force? That force is going to be air drag, okay? So if I want to determine what the force of air drag is, I now just set up F equals ma. Pardon me. So I know that F is going to equal the sum of all my forces. And again, we'll use the convention that upward is positive, downward is negative. And so what I can say is I know that my drag is going to be upward, so I'll use a lowercase f for lowercase f and sub d for drag force minus the force of gravity, and he's descending at a steady rate, so ma is going to be 0 because a is 0. Since they're moving at a steady rate, there's no acceleration, so ma is also going to be 0. So what is the drag force? Well, the drag force is going to equal the magnitude of the force of gravity, or the weight, mg. And so we know what mg was. We were given m. So if we know that this equals the magnitude of my force equals mg, the direction is supplied by my coordinate system, then this is going to be 60 kilograms times 9.8 meters per second squared, and this is going to be very close to 600 newtons. Okay, so the drag force carrying the object upward is going to be very close to 600 newtons. All right. Now, what is well, I'll pause right there for a quick second, right? Again, we know what this value is going to be, how to calculate it, because we knew what the sum of the forces were. In this case, the sum of the forces had to be 0 because the object was not accelerating, okay? So anytime there's no acceleration, you can even have velocity, but as long as there's no acceleration, then ma will always be 0 and the forces must always balance. So if the forces must balance, when there's only two forces, be it tension or air drag counteracting gravity, you know that they're going to be equivalent in magnitude. All right? Now that's not always going to be the case. They don't have to do that. Particularly in the case of air drag, this happens, the balancing of the forces occurs when an object achieves what we call terminal velocity. And that's just the point at which the air drag force is high enough to counterbalance the gravitational force. But when you first jump out of an airplane and first open up your chute, you don't achieve terminal velocity right away. So these forces may not balance right away. So they don't have to balance, but when you're moving at a constant velocity or moving at zero velocity, they will. Now let's do another example, and I now need to introduce two